It's good to see you guys. I hope the quiz went well. Hope it was a little bit easier than the midterm and the last quiz, right? Because it's on some pretty fresh stuff like the sequences and the series, and I haven't looked at them yet. I probably won't until maybe I'll probably get to them tomorrow sometime. But yeah, I really hope no one hope no one mixed up sequences and series on that thing. I'd be really upset if that did happen. But yeah, we got let's see here. We got like 2 sections I need to get through real fast. And whatever I don't get through, I'm probably just gonna put it in the supplemental video, but I'm hoping that I don't have to. We'll see. A couple reminders, homework 7 is due tomorrow. Can you guys please hand in your homework on time and not at the buzzer? Homework 8 and quiz 3 are due next Tuesday. So it's coming up real quick. So the stuff we learned today, the stuff we learned Friday, yeah, that is all fair game for the quiz on Tuesday. I don't think the stuff on Monday will be there, right? 9, 10, 11, right? Yeah, I don't think the stuff on Monday should be on there, but we'll see. I'll play that one by ear. But for sure, quiz 3 is probably going to have like all of the, like using all the tests, you know, you kind of got a taste of that on quiz 2, where I gave you guys, I even told you like which tests to use. I think that like there was like 3, like divergence, integral, DCT. And but on this next quiz, I'm just going to give you the series and you have to determine the tests, you know, so like no training wheels on this one. All right. I think there's a bit of power series on there too. Hopefully I'll get to power series on no, yeah, I should get to power series by Friday, how to deal with power series on Friday. So yeah, it's looking like everything that I covered today and Friday will be on that on the 3rd quiz. Sound good? And of course, your final is next Thursday, which is nuts. We are, guys, we're on lecture 9, and then there's 10, 11, 12, and then we're done. It's crazy. It's nuts. We got a week left. A week left. A week left. It's like over. Isn't that crazy? Aren't you guys gonna miss me? No, it's okay. Don't answer. It's all right. I don't want to hear. So yeah.
Nah, I'm gonna miss you. I'm not even gonna lie, man. When I get to school, I'm gonna be thinking about you, man. Not even gonna lie.
Jeremy,
Like the best teacher ever, bro.
You are too kind, man. You are too kind. I will say though, guy, I mean, like, it's gone like less and less over the years. You know, after I think the first year when I started introducing GroupMe, the students of that year followed up with me like in the fall or in the spring, whenever they took Calc 2, and they asked me questions. They like followed up and like they like revived the group chat, and they were like, yo, can someone help me with this? And then like they post like a homework question, and then like, you know, we'd help them out. It was good times, good times. Wait, it's recording, right? This is recording, right? Okay, yeah. Yeah, I mean, so guys, these videos that I post up, you know, they're gonna, the link, you have access to the links. This class is gonna get archived in Canvas, but you can always go back to it, and these links will always still be there, you know. So let's say you're like, oh man, I remember John talking about like a really nice way to like deal with comparison tests, but I don't remember exactly. You just go back to these videos and they'll be there. All right. Or you just like screenshot a problem, like send it to me as a message, be like, hey John, I know it's been a while, but can you help me out with this problem? Yeah, I'll be like, yeah, sure. So like, I don't know. Use that to your
Appreciate it, man. Appreciate it.
I'm here for you guys. I will always be here for you guys. All right. Sorry, I was getting a little sentimental. So for today, we're going to recap the tests we covered so far. We're going to talk about absolute versus conditional convergence, along with another test, and then the ratio test. So altogether, I think there's like 7 or so tests. So why don't we do a quick recap to kind of, what is it? Just to kind of like, you know, remember like what we've done so far, what we're doing, why we're doing this stuff, right? So quick recap, right? I first introduced sequences, right? It's just a string of numbers defined by some sort of pattern, right? Explicitly defined like function, I guess it's like a function with an n in it. A series is the sum of a sequence, and we're talking about looking for when series converge or diverge. I know I didn't really harp on this, right? I'm sure you guys are curious too, because you guys are such good students. Like, why do we care? Why do we care to know if like series like go to infinity, or like if they diverge, or like, or if they converge? Like, why is this so important? It's kind of hard because I can't really answer that question right now. I'm going to answer it with the next thing that we talk about. There's these things called power series, and basically, what power series are, they're like a series representation of a function. I know that's kind of wild, right? It's like these functions in your brains right now are like these like concrete things that, like, well, it's just an input and an output kind of thing, right? But it's actually kind of nuts because we can define these functions, this stuff with inputs and outputs, with series. And we're going to hopefully get into the thicket of it, because a lot of Calc 2, like the stuff we're doing right now, believe it or not, like the tests and stuff, this is like building blocks. This is like basic stuff. So you, like I say, it's like I'm teaching you how to add and subtract so that I can introduce like variables and like doing stuff with those variables. You know what I mean? So yeah, thank you for Calc 5. Series comes back. So it's like you got to make sure your foundational knowledge of the series stuff is good. Because when you deal with functions that you represent as series, believe it or not, I know this stuff seems complex, but those series are actually much easier to play with than the actual functions themselves. I know it's kind of hard to believe, right? But it's true, right? So recap, we're talking about tests on how to prove convergence, right? I should write that. Tests to prove convergence. I guess I could say, or divergence, right? For the divergence test. Fourier series, y'all gonna hate it. Yes, they are gonna hate it. I've heard, so I'm not an engineer. I'm a pure mathist, all right? But engineers, believe it or not, at some point they diverge. They diverge in terms of like the classes you take. So the pure math people, after Calc 3, split up from the engineers. We say bye to each other. We don't see each other ever again. The pure math people take more theoretical classes, and then the engineers take the engineering calc. So it's like, there's always this argument, like, Calc 4, like, what is it really? Like, I say Calc 4 is like, differential equations. Engineers class, I think it's also called differential equations. Tell me if I'm wrong. Exactly, it's more practical. But I think their Calc 4 is a lot more practical, while our Calc 4 is not as, and then after that we as in the pure math people go into more like proofwriting classes, the fun stuff, right? Proving things using more logic and stuff like that. Whoever fails this class won't be there in the fall. Whoa, that was a little bleak there, man. I don't think they want to hear that. All right. Anyways, tests to prove convergence and divergence. So we start with, I think the first one we talked about was geometric series. Now, geometric series, it's not really called like the test for geometric series. It's just geometric series. It's like it's its own separate category. It's a very special type of series that comes about. We should know how to play with these at this point, right? What are the two things we look for? Somebody?
If the function is geometric, oh.
Okay, whoever, yeah. So Jeremy says your function, you mean your series, right? Your series is because series aren't functions, not yet, at least. Your series has to look geometric. It looks, I'm using that really loosely, looks geometric. What does that mean? It looks like AR to the n, right? And then the second thing, Brandon, what did you want to, did you want to say?
I was talking about the common ratio.
What about the common ratio?
If it's less than 1, but in between 0, then it converges.
Yes, it's convergent. I almost wrote the answer. Yes, convergent. And then if it's greater than 1?
It's a divergent.
Yes. And geometric series is kind of special because this is the only one that can actually tell you what this series converges to. Do you guys get what I'm saying? This is the only one where you can use this to actually find what the sum, S stands for sum, what the actual sum is, if you're in the convergent case. You know what I mean? With all the other series with all the other tests that we've talked about so far, they don't tell you what the sum is. Did you guys notice that? They only say if it's convergent or divergent. Does that make sense? So that's why geometric series is kind of its own like special thing, because in this case, geometric series is the only one that can tell you what the thing converges to, what the series converges to. Next, we talked about the divergence test. I'm shorthanding this because I want to get to the stuff today. So divergence test says What is divergence test for?
Sequences.
No, no. Divergence test is for series. It is for series, not for sequences. Oh no, Dan, did you do that on your quiz? Oh God. Dios mío. Okay. Divergence test, somebody?
Tests for divergence.
Exactly. Yes, it tests for divergence. Divergence tests for divergence. So it does not say anything about a series being convergent. All right. Divergence says you take the limit as n goes to infinity of the sequence part. I hope that's what you meant, Dan. Yeah, is that what you meant?
Yeah, that's what I meant. Yeah.
Yeah, sure. Okay. So you test the sequence part, not the series part. You test the sequence part if it doesn't equal 0. I'm sorry, if it doesn't equal 0, if it doesn't equal 0, the sum of a sub n diverges. This one's a fast and easy one. This is the first one you run on any given series, right? That's not geometric. Up next, we talked about the integral test. This was the really long one. Anyone know what are the 3 things that that need to be true about your function that represents the series or the sequence?
Positive,
Positive,
decreasing, and
decreasing, and
continuous.
continuous.
Yeah. Sing it. Positive, continuous, decreasing. Your f of x that resembles your like f of n, like this needs to be true for that. And then if the integral of f of x dx from whatever 1 to infinity is convergent, then the sum of a sub n is convergent. I'm just gonna, because I'm lazy, I'm just gonna say convergent, divergent, convergent, divergent. If the series follows what the integral does. Yeah, integral test. And what was the thing that I said about integral tests? Like, how do I know when to use integral test? If
If it looks integratable.
if what looks integratable? If what looks integratable?
This series looks integratable. No?
The sequence. If the sequence looks integratable, if your a sub n looks integratable, then yes, you can use, and you should use integral test. Okay. You're like 0 for 2, Dan. Come on, man. All right. After integral test, I mentioned, well, okay, from the integral test came the P series, right? This one was easy. Oh my gosh, what the hell? If it looks like 1 over n to the P, and P is less than or equal to 1, it is divergent. If P is greater than 1, it's convergent. So like P series, like, is it a test? Sort of, I guess, but like it derives from the integral test, so it's like it kind of falls under the same thing. I don't know. So that's what people say there's 7 tests or there's 6 or 8 tests, whatever. After P series, we talked about DCT, which stands for
Direct comparison test.
direct comparison test. If I have a convergent thing and it falls under, then it's convergent. If I have a divergent thing and it falls above, it's divergent. I'm not even gonna talk about that. We talk about LCT. What was LCT?
Limit comparison
The
test.
comparison test.
Okay, what is the limit comparison test say?
Basically, I think you take the limit of your 2 sequences over each other,
Okay, and there's more to that.
and
mean-
the
it
result
means-
will.
Go ahead. Finish
Yeah,
off.
if a of n over b of n is equal to 0, it means something, and if it equals infinity, it means something else.
Okay, all right. I'm not. Okay.
You
All right.
can, yeah.
So for both of these, right? Both of these require you to choose a known like series, right? You guys remember that? That's the first step on both of them. You got to choose one that you know. It could be a P series. It could be a geometric series. It could be an integral test one that you've done before, right? Or that if you want to like prove it through integral test, you can. But it requires you to choose something because, well, what does that C stand for? It stands for comparison. You're comparing 2 things. Your known with your unknown, the thing that you're given, right? So for LCT, you take the limit as n goes to infinity of your known over your unknown, or your unknown over your known. The order actually doesn't matter. And it's going to equal a limit, L. If L is finite and B sub n converges, whoops. then a sub n, the sum of a sub n converges, right? I guess you can say converges or diverges because remember, do you guys remember the reasoning for this, right? It's because if you have a finite limit, then that means they're both growing in the same behavior. They're growing in the same manner. It doesn't matter if the number is 100 or 1,000 or whatever. That just tells you like the spacing, but they're both growing in the same exact way. So if one diverges, the other one also diverges. If one converges, the other one converges. Does that make sense? The other two cases that Justin was talking about, like if your L was like infinity or 0, those don't really come up a lot if you do this correctly, if you do the LCT correctly. If that does come up, usually it means your choice for B sub n was bad. So just make sure you choose a good B sub n when you do a comparison test, right? And I think that was it. Those are all the tests we've covered so far. Yeah, that was it, right? Today we're talking about conditional and absolute convergence. We're going to talk about sort of a different type of series, but not like really different. Oh, I forgot to talk about this. Growth rates. This is going to be important. It's important to know what grows faster than what. For the sole purpose of like this DCT, LCT stuff, when you compare stuff, right, you want to know like what's the fastest growing thing? What's the thing in your numerator, denominator that's going to like take the lead and like, you know, affect the sequence the most. So it's important to know what grows faster than what, okay? So I'm just going to give it to you guys. The order goes like this, ready? ln of n is the slowest growing thing. Think about it. What does the graph of ln look like? It looks like that, right? It looks like it's almost going to be asymptotic, but it eventually does get to infinity. Does that make sense? It like look at the slopes of ln of n, right? It's like steep in the beginning, but then it kind of like tapers off, you know? So in terms of derivatives, speaking in derivatives, right? The derivatives like tend to like go to 0, but it doesn't actually hit 0. You know what I mean? Yeah, no, it's not. Yeah, all right. The next one. The next order is, I guess it's technically, I guess it's technically n to the p ln of n. So it's like when you have ln of n times a power function, or not a power function, like n to some power. You get what I'm saying? Because it's like the slowness of ln of n kind of slows down the power thing, you know? Maybe, kind of, sort of. Next comes, if you have some sort of power that's greater than the n to the p times ln of n, then that's going to grow faster than ln of n. So for example, if I have like n to the third power ln of n, it's going to grow slower than n to the like third plus like 1, you know, n to the fourth power. Does that make sense? Up next is a constant raised to n. You can think of this as exponential, sort of, right? So this is like exponential. And that should make sense, right? What does the graph of exponential look like versus a cubic, versus a quartic, versus a whatever, right? As you go off to infinity, exponential will beat any power. Up next is the factorial function. You guys know what factorials are? Did Gina talk about factorials with you guys? Factorials comes up a lot. Do we know how to play with factorials?
Not really how to play with them, but kind of know what they are.
Okay, when it comes across, then I will, I'll take my time with it then. And the very, very fastest growing thing is n to the n power. These are the most common ones that you'll come across. Questions on this? So why is this important? So you could do problems like this. Whoops. Oh my gosh. I'm sorry, guys. I'm rushing. It's so you can do problems like this. If I have oh man, John, you didn't teach us how to do that. What's the first test we always run? Oh my gosh.
Divergence test.
What's up?
Divergence test.
Divergence test, which says that I'm going to take the limit as n goes to infinity of n to the n over n factorial. Well, Now that I know my growth rates, what grows faster, the top or the bottom?
The top.
What? Did you see the bottom?
The top.
The top. He said the top, everyone. He said the top. So that means this thing goes to,
Infinity.
which is not 0. So we can say by divergence test, I forgot to label this thing. Sum of a sub n diverges. Boom. Nice and easy, right? This is why growth rates are really important. If it was flipped, if it was n factorial over n to the n. By the way, don't say n. Don't say that. Okay, people will laugh at you. All right, don't do that. All right, but if it's n factorial over n to the n, we need a different test because that would equal 0, and then we need to run something else. You guys see that? Okay. All right. Whatever. So let's move on to 10.4, which talks about absolute conditional convergence. So we're going to take a pit stop here because this section deals with non-positive terms. So they could be negative or they could be 0, but we're basically talking about negative terms because if you think about it, right, the series that we've been playing with so far have all been positive terms, right? So if we want negative terms to appear, we're going to need to introduce a good friend of mine here. This guy has a very special name. You're going to hear this a lot. It's called the alternator. Did I spell it right? Alternator. I think I spelled that right? Why does that look weird? Is that right? Alternator.
It does look weird. I don't know why, but it does.
Okay, I think that's the right spelling. Let me know if I'm wrong. But alternator, okay? We are not talking about the thing in your car that starts your car. This is something else, all right? Think about it. If I plug in values of n, what's going to happen to this thing?
It's either going to be positive or negative.
This is the thing that it's like, you can think of it as like a light switch. It turns on and off, positive, negative, positive, negative, positive, negative, positive, negative, right? So when you see these bad boys in series, right? Just know that that's what it means. We're dealing with non-positive terms. Okay? Sound good? So if you hear me say the word alternator, I'm not talking about a car, I'm talking about the series, right? So, absolute convergence. So let's talk about this first. Absolute convergence. What the heck does this mean? Well, when you hear, an easy way to remember this is the word absolute. What do you think of when you hear the word absolute in math? In math.
Absolute value.
What?
What Jeremy said.
What did Jeremy say? You guys like talked at the same time, so I didn't.
I said absolute value.
Absolute value, right? That's what this is talking about. That's the way you can think about it, right? Absolute value. So there's actually a theorem. We are on page, I think it's 585 in the PDF. I'm pretty sure it's 585. But there's a theorem that basically says if the sum of absolute value of a sub n. Okay, no worries, man. Just what is it? Catch it on the video then. If the absolute value of the sequence, I almost said series, sorry. If the absolute value of the sequence, right, and you take the sum of it, converges, then the sum of regular, like without the absolute value, also converges, but we add an extra word, we say absolutely. So what does this mean? If I have a sequence that's alternating, so I got terms that are flipping back and forth, back and forth, back and forth, right? But if I negate all of the negative terms, if I make everything positive, because that's what absolute value does, right? It turns everything positive, and that thing converges, then the one that's flipping back and forth will also converge. Do you guys get what I'm saying here? You don't have to get the why, you just have to get the what right now. Yes? Do you guys get what I'm saying here? Do you need an example? I'll show you guys an example. So 1 over n squared with an alternator. So let's call this example 1. From 1 to infinity. So we're looking at this thing. This theorem is basically saying, if I have, if I look at the sum from n equals 1 to infinity of 1 over n squared, do we know anything about this thing right here? Do we know?
Converges.
Why Don't just say
P
converges.
series.
Right. We know if I call this A sub n, this is converges by P series. Right? If this is true without the alternator, then with the alternator, we can say the sum of, did I screw this up? Oh, I'm sorry. Yeah, this is the sum of, okay, and then this is A sub n. So with the alternator, it's A sub n. And then like the absolute value thing will get rid of the alternator. You guys get what I'm saying? So we say since the absolute value of A sub n, taking the series of it, converges, the sum of A sub n, or I'll write it out just for this one, with the alternator, converges. Absolutely. Do you guys see that? Do you have any questions? No? This makes sense? Are you sure? Absolute convergence is a little confusing, I know.
Yeah, I'm trying to wrap my head around it.
Okay.
Wait, does absolute convergence stuff only apply to a series with the alternator in?
Because remember, like I said, we were playing with just positive series before, but now we're throwing in negative terms and seeing how that influences our series. Yeah. Let me draw you guys a picture. Hopefully this will make sense. Ready? So 1 over n squared, it looks like this. The terms are going to do this. Right? You guys know what 1 over n squared, the graph looks like. It looks like a hyperbola, but it's like, it's on both sides. It looks like this. You know what I mean? Oh God, but you know what I mean, all right? That's what 1 over x squared looks like, right? But 1 over n squared, the terms, it's basically saying 1 over n squared is convergent, right? But if this is 1 over n squared, but if I look at 1 over n squared with an alternator in it, think about it. Every other term gets like flipped. It goes to the negative zone. Do you get what I'm saying? So that means you can say like quote unquote half the terms become negative. Well, if I have half the terms that are negative from a convergent series, well then that means what?
It also converges.
You guys see that? Oh, wait, did I screw that up? Wait, no. Yeah, no, that's right? Right? Yeah. 1 over n squared is convergent. With the alternator, it's going to be smaller than 1 over n squared. Therefore, sorry, there was a fly. Therefore, that is also going to be convergent because it falls under. We don't need to check it. It's going to fall under. Are you guys with me here?
Yeah. That makes perfect
Makes
sense.
sense? It makes sense? Good. Anyone? I got it. Oh, I got it. It's on my pad now. Gross. Sorry, hold on. All right. Sorry. Anyone have questions on this idea of absolute convergence? No. So then let's talk about conditional convergence, because something weird happens, right? So we talked about if this thing is convergent, but what happens when, what happens when your absolute value of a sub n is not convergent, divergent? So we need to talk about this. Before I do conditional convergence, I'm going to talk about a new test. Alternating series theorem, alternating series test. AST for short. Ready? Alternating series test is on page 587. Page 587 on the PDF. Alternating series test says, okay. This is really wordy in the book. I'm gonna just make it really easy for you guys, okay? Assume you have given -1 a sub n. So basically you have an alternating series. That's all, right? And that should kind of make sense. Alternating series test, you use it for alternating series, duh. So given this thing, if two things need to be true. If a sub n is decreasing, meaning the terms are getting smaller and smaller and smaller and smaller, right? This means a sub n plus 1 is smaller than a sub n, right? You don't need a dot dot, sorry, I don't know why I did that. And the limit as n goes to infinity of a sub n is equal to 0. Then, oops. Then the given series converges by AST. What is this saying? So it's saying if my terms, so long as my terms are getting smaller and smaller and smaller, right? And the limit as the sequence goes to infinity eventually goes to 0, this thing has to converge. The way you can kind of make sense of this, the way you can like be convinced of this is just, it's the same picture. Like look at the picture, right? This thing, the black sequence is decreasing and it is going to go to 0, right? But if you think about it, if we're taking half the terms and subtracting it from any sequence that has these two characteristics, it's gonna converge to a finite value. Do you guys believe that? Can you guys like convince yourselves of that and believe that? Does that make sense? Think about like make sense out of it. Why wouldn't an increasing function work? I'm sorry, not function, sequence. If the sequence was increasing, why wouldn't that work? Or if it wasn't decreasing, why wouldn't that work?
Because it's not going to a finite value.
So I'm saying like, I'm drawing a picture here. So I'm saying like, if it wasn't decreasing, if it wasn't strictly decreasing, so it was like this, and then it went down, but then like it went back up, and then like it went up some more, and then it kind of went back down. You know what I mean? And like, if it wasn't strictly decreasing, why couldn't we say that this also converges? Is my question not making sense? Or do you guys get what I'm asking? No?
Yeah, I'm just not sure how to properly answer.
Yeah.
It's because then some of the terms will be like skyrocketing off the place. You can't confirm that it will converge. You can't. No, does that make
Yeah, I
sense?
guess you're saying like it's not predictable, so you don't know like if everything will fall underneath,
Exactly.
right?
Yeah,
Yeah.
pretty much, right? And the second part makes sense too, right? It has to eventually, the sequence has to go to 0, because if it doesn't go to 0, if it goes off to some other number, you're going to be adding up some number. So it's like if I had a sequence that like act asymptotically to like, I don't know, let's call this like -2. That means eventually you're going to be adding a bunch of -2s, and it's going to diverge off to negative infinity. Do you get what I'm saying? That's why it has to go to 0. It can't go to anything else. It can't go to 0.1, because then you're going to be adding a bunch of 0.1s infinitely, and that's going to go to infinity. Do you get what I'm saying here? So hopefully these two criteria make sense, like why this needs to be true. All right. So now that we have an idea of how to prove alternating series, let's talk about conditional convergence. All right. So we know what absolute convergence is. Let's talk about conditional convergence. Now, this is going to get a little confusing because we talked about absolute convergence and we talked about the AST. So please like ask me questions. All right. So here we go. I'm going to just do a really simple example. Ready? Let's look at the alternating harmonic series. We're looking at the alternating harmonic series. Well, if this is my A sub n with the alternator, let's look at what's going on with the series without the alternator. What do we know about this?
It's continuously decreasing.
Okay, it's decreasing. I'm talking about, but I'm talking about this guy right here.
Diverges by p-test,
Okay.
p series.
Yes, this is, we know that this is divergent by P series. Also, it's the harmonic series, and we know the harmonic series diverges. You guys with me so far?
Yeah.
Something really interesting happens here. If we look at the original series and we run the AST test, we actually get a convergent series here, right? Watch. We know A sub n is decreasing, right? 1 over n is greater than 1 over n plus 1 is greater than 1 over n plus 2, and so on and so forth, right? You don't have to prove it. I'm not going to ask you guys to do that. And then we also know limit as n goes to infinity of A sub n is equal to 0. Just a side note, when you're running AST, you need to say these two things. You need to make sure that's in your work, okay? Sorry, this is example 2, I think. You need to make sure that you state your assumptions, okay? So please make sure you don't forget to do stuff. That's why I'm starting it. So we can say, so by AST, the sum of A sub n is actually convergent. Do you guys see what we just did here? We said this thing grows too fast. It goes to infinity. But as soon as you tack on the alternator, right, half the terms take away enough for this thing to converge. Snap. No? I feel like you guys just really just don't care. Isn't that nuts? We took something that went to infinity and then made it like finite by like taking away like half its value.
Would you be able to like graph it or draw it out so like I can picture it better?
I'll be honest, Brandon, it's literally the same picture as this one. But yes, I will do it. I'll do it just for you, Brandon. All right. It's because I like you so much. So 1 over n looks like the first term is 1. This is let's say this is -1. So the first term is 1. The second term is -½ The third term is like third, and then it's like fourth, and then fifth, and then and so on and so forth. Right? So it's basically like all we're doing is we're adding this with this, with this, with this, with this, with this. The idea is the negatives are enough to take away from the positives and make this a finite value. That's all I'm saying. That's what we're saying. Maybe should I color code it? Here, I'll make the negatives red. Maybe that's more fun. Okay. Yes.
I think, yeah, I think I can understand it now.
Okay, cool. Great. Anyone else have any questions on this? I haven't made my point yet though. This is the point I'm trying to make. If you have something that diverges without the alternator, but then something that converges with the alternator, we have to say that it converges conditionally. What's the condition? That there's an alternator.
Oh, you beat
no.
me right to it. You beat me
Fake.
to
You fake. You fake. You're lying. You're lying. All right. All right. Do we understand? So absolute convergence is when the series converges with the absolute value, right? So it's like absolute convergence is like the thing converges, so the thing under it will converge, right? So the given one will converge. Conditional convergence is when you have to use AST, right? The conditional convergence is when it's divergent without the alternator. So we don't know, right? And then with the alternator, it's convergent on the condition that, so we have to state conditional. Do we have to say absolute and conditional for all of them now? No. If your series is positive, you don't have to say absolutely. It's just, you just say it converges, right? But once you have an alternator in there, you have to check for conditional or absolute convergence. So that's why this is all in one section. It's all talking about when you start introducing negative terms. You guys see how it all connects? Yes? How are we doing? How are we doing with absolute convergence? Conditional convergence? Can you guys give me a thumbs up in the participant thing if you're following along? Yeah. Okay. All right, you guys are on the camera. Thank you for showing me your thumbs. Appreciate it. Appreciate it. Appreciate it. Awesome. Cool. So that's it. That's honestly, that's the bulk of 10. 3. Is this 3 or 4? I think this is 10-4. 10-4. That's the bulk of 10-4. There is one last thing it goes into. I wish I could do this with you guys, but there just isn't time. There's something in 10-4 on page 588. It's it lets you know if you have okay, so if you have an alternating series that converges, right? So on page 588, if given an S which is equal to 1 to infinity or -1 to the n b sub n. They use b sub n, I don't know why. But if given this, and this is it's positive, decreasing, and goes to 0, b sub n. If given, so basically what this means is if given a converging alternating series, if you give in an alternating series that converges, you can actually figure out how much error you have if you go to a certain amount of terms. So it's like, if I go to like 6 terms, right? It's gonna spit out a number, right? It's gonna say like the sum is like 1.7 or something like that, right? But we know that's not the actual sum, right? It's pretty close because it's 6 terms. But the thing is, this series goes off to infinity, right? We're missing an infinite amount of terms. So there's this thing that that tells you how much you're actually off by, which means that you can figure out like the sum of these alternating series. So I'm not going to talk about this today in this thing. I'm actually going to do that in the video. It's called the alternating series. I think it's usually called like the error bound. Error bound. So different people call it different things, but I usually call it the error bound. This is not going to be in this class. I'm not going to force you guys to learn this because it is a little, it's very interesting, but it is a little annoying. But this is something that will come up when you take this class. So definitely look to the video, it's going to be there. If you ever need to go back and learn the alternating series error bound, okay? But I'm just going to move on. Sound good? All right, so we talked about conditional absolute convergence. Let's talk about this last test. We're in the last test, and then we can talk about power series. Section 10.5. It's called the ratio test. You guys are gonna love this one. It is tremendous. It's very good. It's it's a very fun one. It's a very easy one. This is like, you're gonna love this one. Okay. Now 10.5, it also goes into the root test. We're not really going to talk about the root test. The results of the root test are the same exact as the ratio test. It's not that hard, but I really don't feel like talking about it because it's just time. All right. So root test, don't worry about it. I think they do it. They do this in the class, but I'm not really gonna. It's pretty straightforward. So ratio test. Here we go. So how do I say this? Given a series, okay? Given a series. There's this Greek letter they use. I know it looks like a P, but it's actually called rho. It's like a lowercase. It's lowercase triangle. Forget it, whatever. But it's a letter they use a lot. But it's this called rho. Don't say P, right? Because then you're gonna get confused with P series and all that stuff. It's rho. So let's say we take the limit of this guy right here. They tack absolute values on there, but if you're playing with the positive series, you don't need the absolute values because then it's just redundant. If you haven't, you can use this on alternating series though. You can absolutely use this on alternating. I would highly recommend though, using alternating series test for the alternating series first. Did you guys catch that? So if given an alternating series, Run the AST first and then do the ratio. Yeah? Yeah? Okay. What are we doing for this? What is this saying? Right? You know what? I'll just give you the outcomes right now. If rho, there's 3 outcomes. If rho is less than 1, the series converges. I guess you could say absolutely if you want to. If rho is greater than 1, it's a rho. It's a rho, not a p. It diverges. The series diverges. You guys understand why we don't say diverges absolutely, right? If you diverge, you diverge. There's no absolute. It's like, it doesn't matter. Does that make sense? Yeah, so don't say diverges absolutely. It's not a thing. And then the third outcome is if rho is equal to 1, the test is actually, oh my gosh. The test is inconclusive. Bum, 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 bum. Okay. Did you guys get this down? Can I talk? Can you guys, are you guys listening? Yes?
Yeah.
Okay. So listen up. What is this saying? Why is this true? Why does this make sense? Well, we got to talk about what we're doing to figure out rho. Here, I'll zoom out so you guys are still copying. We got to talk about what exactly are we doing to figure out rho. Let's think this through, okay? We are taking a sub n plus 1 and putting it over a sub n, right? The series, it goes like a sub 1 plus a sub 2 plus a sub 3 all the way out to a sub n plus a sub n plus 1 plus all the way out to infinity, right? What are we doing when we do this? Anyone?
When we're doing what specifically?
When we're doing this action in red, putting a sub n plus 1 over a sub n.
Putting the next term over the previous term.
Right, we are good.
Seeing if it increases or decreases.
Seeing if what increases or decreases.
The series, well, the sequence.
The sequence. Okay, fine. That's good enough. All right, fine. What we're doing, thanks, Dan, by the way. What we're doing is, think about it, right? So before with LCT, right? We would compare a sequence that we know with the sequence that we don't know, right? But for the ratio test, we're comparing the sequence with itself. Whoa. You guys see that? Yeah. We're taking the next term, putting it over the previous term, and when we let n go to infinity, we're seeing, is this thing eventually going to grow uncontrollably? Or is this thing going to eventually stop growing and hit a constant value? No. If the rho value is less than 1, meaning it's a fraction, meaning the comparison between the two is getting smaller and smaller and smaller, then it should make sense that the terms will eventually shrink and shrink and shrink and shrink and shrink, and then eventually converge. If the rho value is greater than 1, that means when you compare the two things, the next term it's growing too much faster than the one before it. And it's growing and growing and growing and blows up to infinity. Do you guys get that? Does that make sense? So here's $1 million question. What is that third statement saying? Why is there an inconclusive case then?
Means that it's stagnant.
Because it's stagnant? Okay. Like why would that be an inconclusive case?
Wouldn't that mean the number in front of A of n is the same as A of n?
Oh, Brandon from downtown. He shoots, he scores. Yes. If the number, or think about it, guys, if the number and the one before it are the same. So here, let me give you 2 super duper easy examples here, right? If I look at versus, oh, sorry, that we just did that. Come on. Okay, if I look at these 2 examples right here, right? and I take the ratio of this thing. The ratio, I know you can't divide by 0, but I'm saying if you just look at it just to fulfill this example, the ratio is not changing, right? It's going to be 0 plus 0 plus 0 plus 0, right? Obviously, you can't take the ratio of 0 over 0 because it's like algebraically, but it's not changing is what Brandon just said, right? But we know that this is what? If I add an infinite amount of zeros, what is it going to be? Is it going to converge or diverge?
Converge to 0.
It's going to converge. If I look at the other case, if I add up 1 an infinite amount of times,
Oh, it's gonna diverge.
so this is why this third stipulation exists, because there can be sequences that do this, right? Where the ratios will be the same, but we don't know if it's going to converge or diverge. So we got to run a different test. Does that make sense? Yeah. Cool.
Yeah, that makes sense.
Cool. Do the first two cases make sense, right? If the ratio is less than 1, it's shrinking and shrinking and shrinking and shrinking, and then we'll converge. If the ratio is greater than 1, it's going to get bigger and bigger and bigger and bigger and diverge. Yeah. Pretty easy test, I know. Last thing I want to say about ratio test, it's a trick. Ready? When you see factorials or n to the n, don't even, well, after you run divergence test, right? Because divergence test you always run first. Don't even bother with the other series. Use ratio. Use the Horatio test. Sorry, I misspelled that. Okay. When you see factorials in your sequence, when you see n to the n in your sequence, use the ratio test. Do not even bother with the other stuff. You guys good so far? You guys ready to try an actual example now? All right, I'm gonna do one with the factorial because I know you guys are not so good with them. Here we go. Ready? I'm just, you know what? I'm gonna tweak. I'm gonna tweak example 3. This is the one on page 592, but I'm gonna tweak it also slightly so we get a little bit more practice with factorials. N equals 0 to infinity. And oh, this is it deals with what we just talked about too with absolute and conditional convergence. So watch. And let's do n plus 2 factorial over 1,000 to the n times n factorial. You guys ready? So imagine this is a test question. I'm given this problem. Holy crap, John must really hate us. Okay, after you pass that, right? You get to the alternator, you're like, okay, maybe I can run AST. Or maybe I could run divergence tests, but they're conflicting, what is it, factorials happening and stuff like that. You know what? I'm just gonna run the ratio test because I see the factorials and I see the to the n power. That's fine. That's what you should be thinking. Okay. The reason why we can do ratio test is because what was I saying? Oh yeah, is because ratio test those absolute value bars, right? If we can prove what is it? Absolute convergence, then we don't have to worry about this thing, the alternator. You know what I'm saying? Does that make sense? Do you guys remember what we just talked about in the last section, right? So let's do it. Let's run the ratio test. So we say the limit as n goes to infinity, I am going to disregard the alternator because like I said, if the absolute value of a sub n converges, then the whole thing will converge. I'm actually not sure if this thing is actually going to converge. It should converge. But let's see, here we go. So I'm going to run the ratio test. Ready? How do I do it with factorials? Ratio test says replace all the n's with n plus 1s. Replace all the n's with n plus 1. So this becomes n plus 1 plus 2 all inside a factorial, or n plus 3 factorial. You guys see that? On top? Did I lose anyone? I'm just replacing this n with n plus 1. Yeah? On the bottom, I get 1000 to the n plus 1 times n plus 1 factorial. Anyone confused? This is my a sub n plus 1 term. Yeah? Anyone lost? Okay. Well, ratio test says I got to take my a sub n plus 1 and put it over my a sub n. This given thing here, right? But that is the same thing as keep, change, flip, isn't it? If I'm dividing by a fraction, keep the first one, which I just did. I'm going to change the division to multiplication, and I'm going to flip, keep, Chanji, and flip the original, which is 1000 to the n factorial all over n plus 2 factorial. Man, this one's dirty. I didn't mean to do you guys dirty like this. Sorry. But I'm interested to see what the results. So let's see what happens. You guys ready? Here's the fun part. Let's cancel stuff out because we can. So this becomes, I'll do the cancel. I'll do the work in blue. What the heck? Oh. This becomes n plus 3 factorial. And okay, so let's try and cancel some stuff out here. Ready? So I have a 1000 to the n power on top, and then I have a 1000 to the n plus 1 power on the bottom. So that leaves me with a, this is the same thing as 1000 to the n times 1000, right? Exponent rules. You guys remember those? So the 1000 to the n's actually just cancel out, leaving you with 1000 on the bottom. Yeah. This next part's going to be new for a lot of you. How to cancel out factorials. So watch closely. All right. I have an n. Okay, let's deal with the n plus 3 factorial first. No, let's deal with the n factorial first. This guy. I have an n factorial. I have an n plus 1 factorial. Well, n plus 1 factorial is the same thing as n plus 1 times n minus 1 times all the way down to 1. You guys, that's how factorials work, right? You keep subtracting 1 from the thing until you hit 1. N factorial is n times n minus 1 times n minus 2 times all the way down to 1. So what's going to cancel out?
All the n and below.
N and below. So that kills that. This kills that. That kills all of that. You guys see what I did there, right? So what are you left with? You're left with an n plus 1 below. Don't forget about that 1000. Let's do the other one now, right? I got an n plus 3 on top. So that's n plus 3 times, I should have done this in blue, sorry, whatever, times n plus 2 times n plus 1 times n times all the way down to 1. Whoops, that's a 1. What is n plus 2 factorial? That's n plus 2 times n plus 1 times n minus 1 times all the way down to 1. What's going to be left over?
The n plus 3.
Only the n plus 3, right? The n plus 2 and down all get canceled out. Does that make sense? Yeah, is that okay? All right, good. Whew, a lot of work here. Let me clean it up for you guys. This is the same thing as, well, what's left on top? It looks like the n plus 3 is left on top, right? Nothing else was left over on top. It looks like a war zone. On the bottom, what's left over is 1000 and an n plus 1. Can someone just double check that? Is that, those are the only things left over, right? Yeah? We good, right? What happens when I apply this limit now? I have an n plus 3 on top and n plus 1 on bottom. Ooh. What are those two things going to do?
Both go to infinity.
The 3 and 1 are going to basically be irrelevant.
Okay, all right. They are both, we talked about this also, guys. Come on. They're both growing the same rate. N plus 3 and n plus 1 are growing at the same. So this and this are it's gonna go to 1. Leaving you with 1/1000. This is the rho value. And oh my gosh, that's it. Since rho is less than 1, the series converges.
Absolutely.
Okay, fine, absolutely.
Oh, via the ratio test.
Oh, thank God. By the ratio test, guys, please don't forget to mention the test that you use. Whatever test you use, you have to say it at the very end. That's how logic works, okay? Yes, that's it. That's how a ratio test works. This one was a little bit beefier. I didn't mean to start you guys on like 7. I wanted to do a problem that was like a 3, but the reason why I wanted to do this one is because there was factorials in it, and I know some of you have never seen factorials before, especially with the cancellation stuff. So it's here, but most of the problems are going to be pretty much in the same manner, right? You figure out the row, there's going to be a bunch of cancellation. There's going to be a keep, change, flip thing that you do, and that's it. Those are all the tests. Yay, 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 nay, maybe, no. All right. Okay, well, it's 4:53. Sorry to keep you guys. If you guys have any questions, I think tomorrow in recitation, Gina, I'm gonna tell Gina to go through like a buttload of problems with you guys. Also as preparation for your quiz next. I can do it Tuesday, right? I said Tuesday, I think. Right. So your quiz is next Tuesday. Like I said, I'm gonna give you a random series. You have to pick one of the tests to use. Has to be the right test. All right. There's a section in the book. It is section 10.7. I think it's a 10.7. No, it's not. Where is it? Damn it. I'll let Gina know, but there's a section in the book, kind of like, you guys remember when we were learning the integration techniques? There was a section that said, like, this is how you choose like integration techniques and stuff like that. I'm pretty sure there's a section in here that has that for choosing what test to use for series as well. All right. Also, under resources, I'm going to put it up after class today. Under resources, I'm going to put up like this flow chart that basically tells you like what tests to run. And on that flow chart, there's like additional practice problems too. Take a look at it. Look at the problem, be like, I think I'm going to run this test, or I would run this test, and so on and so forth. It's just good practice to kind of build up the intuition for this stuff. All right, sound good? Thank you guys for staying. Have a nice day, and I'll see you guys on Friday.
Have a nice day, John.
All right, have a
See you
nice
Friday.
day.
See you. Have a nice day.
Bye, bye, bye.
Everyone.